I'm not going to do that to you guys. Okay, let's pray. Okay. Lord God, we thank you so much for fun and laughter and fellowship and silly pictures. Thank you for lining up Connor's head with that penguin. We appreciate it, Lord. And I ask that you help us to absorb new information today, to make use of our brains. Uh, and I pray you'll help us honor and glorify you in how we do that today. We pray in your name. Amen. Okay. I'm just going to pick somebody today. Let's see. How about who hasn't read? Hey, Shepherd, would you please read our devotional this morning?
Sure.
Okay, go for it.
Okay, do you want me to start with the verse?
Yes, please.
Okay. I will cause the shower to come down in his season. There shall be showers of blessing. Ezekiel 34:26. Here is sovereign mercy. I will give him to the shower in its season. Is it not sovereign, divine mercy? For who can say, I will give him showers except God? There is only one voice who can speak into the clouds, and bid them beget the rain. I don't know what that word means. Who sendeth down the rain upon the earth? Who scattereth the showers upon the green herb? Do not I, the Lord? So grace is the gift of God, and is not to be created by man. It is also needed grace. What would the ground do without showers? You may break the clods, you may sow the seeds, but what can you do without the rain? Is absolutely as absolutely needful is the divine blessing. In vain you labor until God, the plenteous shower, bestows and sends salvation down. Then it is plenteous grace. I will send them showers. It does not say I will send them drops, but showers. So it is with grace. If God gives a blessing, he usually gives it in such a measure that there is not enough room to receive it. Plente Plenteous grace. Ah, we want plenteous grace to keep us humble, to make us prayerful, to make us holy, the plenteous grace to make us zealous, to preserve us through this life, and at last to land us in heaven. We cannot do without saturating showers of grace. Again, it is seasonable grace. I will cause the shower to come down in its season. What is thy season this morning? Is the season of drought? What is the season of drought? Then that is a season for showers. If is it a season of great heaviness and black clouds, then that is the season for showers. As thy days shall as uh, as thy days, so shall thy strength be. And here is a varied blessing. I will give thee showers of blessing. The word is in the plural. All kinds of blessings God will send. All God's blessings go together, like the links of a golden chain. If he gives converting grace, he will also give comforting grace. He will send showers of blessing. Look up today, O parched plant, and leave thy leaves and flowers for a heavenly watering.
Okay, thank you. Man, isn't that comforting and encouraging? No, Lydia, it wasn't you. You see the lovely background that Ian and Grayson are sporting today? That was Owen. Owen captured the perfect moment. Connor's head was a penguin. So that's all him. Yeah. Yeah, I know it was you, Owen. Okay. It is really funny. Okay, guys. So we are going to keep talking about module 12 today. So I am not quite done with all the grading. I'm racing. I betrayed you. I don't know. I think Connor could more fairly say you betrayed him. Right. Okay. So I'm racing to finish grading. I'm almost done with all the labs. The test will be much faster, so I'm working hard here. So what we learned about yesterday is how to talk about heat energy when it comes to chemical reactions. And we learned what heat actually is, right? Heat is kinetic energy of the molecules. And then we learned uh, that how temperature is different, right? We'd already talked about it before. So we know that heat is kinetic energy of molecules, and then temperature is a measure of the average kinetic energy. And we know about specific heat capacity. Now, Connor, he's going to be at call. You can take him down then. It'll be fine. I'm going to make it an NSA's problem, this conflict between you guys. Duke it out, right? Duke it out. Okay. So we learned this equation, Qmict, right? Cubert's cousin, and it allows us to calculate the heat that is either released by an object or absorbed by an object. If we know its mass, we know its specific heat, and we know its change in temperature, right? Or if we have any three out of those four, we can calculate the fourth. So today, what we're going to do is learn how this equation can be used in a lab to do a real world measurement of the heat that is released or absorbed by something. Okay. And that is, oh, hold on. It's a process called calorimetry. Okay. So calorimetry, calorie obviously being a unit of heat energy, and then metry refers to measuring. And so calorimetry takes advantage of the uniqueness of water. So we know already that water has a very high heat capacity in comparison to a lot of other things. And so there's two different types of calorimetry. One we call a coffee cup calorimeter. And the reason we do that is because it's usually two styrofoam cups that are nested inside each other. So I'm just going to let everybody who lives in Washington know you're going to be a little bit irritated when it's time to do the lab because guess what you can't buy in Washington State? Styrofoam cups. So the best thing to use, because you know they're bad for the environment. Um, so you can use an insulated coffee cup. Like there are paper insulated coffee cups. So yeah, they're illegal in Washington State. I discovered this last year when it was time to do the lab demo and I couldn't find any styrofoam cups. So there might be other states this applies to as well. I don't know if you can buy them in Oregon. Lydia, Ian, you'll have to let us know if you can find styrofoam cups. Just drive to Idaho. It'll be fine and get some styrofoam and come back. So a coffee cup calorimeter is really good either for small objects or for reactions that can happen in aqueous solution. And you use two cups so that the outer one is acting as an insulator. You fill the inner one with water. You put some kind of insulated stopper or lid on the top. And then you stick a thermometer through that and then also something to stir with. The reaction happens in the water. The temperature changes and you can measure it with your long thermometer. Okay. Now, there's also one called a bomb calorimeter. And while this would be really awesome, none of us own a bomb calorimeter. This is the kind of thing you'd only find in a fancy chemistry lab. And it's used to calculate Q for combustion, right? But it uses a similar principle where you have a chamber where the combustion reaction can happen, and it is surrounded by a water jacket, right? So you're still measuring the temperature of the water and you're able to figure out how much heat either was lost by the reaction or gained. So this whole thing, calorimetry, uses a specific mass of water and the principle of thermal equilibrium. Thermal equilibrium. So this graphic here illustrates thermal equilibrium. So remember our definition of heat. Heat is energy that is transferred as a result of temperature differences. So if you put two things next to each other that have different temperatures, heat energy is going to leave the hotter one and transfer to the less hot one until they're both at the same temperature. Okay, that's thermal equilibrium. So it's reached when the net movement of heat, the net flow of heat is zero. Nothing's moving from point A to point B. Nothing's moving from point B to point A. No need because they're all the same temperature. So that means that the net flow of heat is zero when the water, the calorimeter itself, and the object have all reached the same temperature. Did you have a question, Gunnar?
Uh, yeah, but it doesn't matter anymore.
Okay. Well, if it becomes relevant, let me know. So let's think about in terms of calorimetry. What this means is we have an object that is at a particular temperature. It transfers heat to the water and the calorimeter. And then at the end, the object, the calorimeter, and the water have all reached the same temperature. So when we're calculating delta T, the object is going to have a different initial temperature than the water and the calorimeter, but they're all going to have the same final temperature. Okay. This right here, what I just said, is the thing that trips people up the most. It's knowing which temperature applies to what. Okay. Everybody gets the same T final, but the object and the water and calorimeter will have different initial temperatures. Okay. So here is what we call the calorimeter equation. And all it says is the heat that was lost by the object was gained by the water and the calorimeter. Okay. Or if it was a cold object that was put into warmer water, the energy that was gained by the object would be what was lost by the water and the calorimeter. This sign here is really, really important. It's also why it's really important that your delta T have the proper sign. Okay. So we're going to do a couple of examples and you'll see why that is. Okay. So just a refresher on the temperature. So I've got a little object and it's sitting in water inside a calorimeter. The object has its own T initial. Okay, so for this situation, we're talking about where a hot object is dropped into a calorimeter to measure how much heat energy it's got. Okay, the water and the calorimeter have the same T initial. Okay, and at the end, everything has the same final temperature. So delta T for the object is equal to the final temperature minus just the object's initial temperature. Okay. And delta T for the water and the calorimeter is equal to that same final temperature, but minus its initial temperature, the water calorimeter initial temperature, and it's different. Okay. So before we start the problems, I'm going to show you guys something. I made a little chart here. When you're doing this type of problem, the hardest part is reading this problem that has 12 numbers in it and figuring out what they belong to. Like, what does this number represent? So we're going to use this little chart when we're doing practice problems, and I want you to make something similar for yourself. When you're reading a problem, make a little note of, okay, I need to know what applies to the object, to the water, and the calorimeter. And I need to know mass, and I'm going to need to know the final and the initial and any values for C. This obviously you're going to be calculating. Although sometimes the problem is going to give you an initial temperature and a delta T, or a final temperature and a delta T, right? We saw that yesterday. So you need to be able to fill in as you go. So I'm going to show you how easy it is when you do it this way, okay? All right, let's try our first example. So I'm going to make us a stickum note, okay? And I'm going to get our little chart. Boop. Okay, so here's our chart. So let's read this. A chemical reaction is carried out in a 5-gram calorimeter. The calorimeter has a specific heat of 1.95 joules per gram degree Celsius and is filled with 150 grams of water. If the temperature of the water was 24 degrees Celsius before the reaction took place and it rose to 32 degrees Celsius by the end of the experiment, how much heat was released by the reaction? Okay, don't have a heart attack. That was a lot. But let's go back and fill in things where they belong. So because this is saying a chemical reaction happened in the calorimeter, we don't have a mass of the object, okay? We're going to ignore that essentially, but we're still going to be able to figure out what it's asking, which is how much heat was released by the reaction. Okay, a chemical reaction is carried out in a 5-gram calorimeter. That means the calorimeter has a mass of 5 grams, right? That's all that means. Okay, the calorimeter has a specific heat of, okay, so this is the C value for the calorimeter. Okay. And it is filled with 150 grams of water. Okay, well, there's the mass of water. Okay. If the temperature of the water was 24 degrees Celsius before the reaction, okay, so that word before is a good indicator that that's our initial, right? That's at the start. So the water has an initial temperature of 24 degrees Celsius, and so does the calorimeter. The water and the calorimeter are always going to have the same initial temperature, right? Okay. So the temperature of the water was 24 degrees before, and it rose to 32 degrees Celsius by the end of the experiment. Okay, so there's a final, right? There's a final temperature for us. So that's 32 degrees for the water. It's 32 degrees for the calorimeter, and it's 32 degrees for the object too. Final temperature always the same for all three. Okay. Now the question is how much heat was released by the reaction? So what we're looking for is the Q of the object, right? Or object or reaction in this case, interchangeable. Okay, guys, this was actually the hardest part, was getting our little chart filled out. And we can also now calculate our delta T. So delta T, right, is always final minus initial, okay? So for the water and the calorimeter, it's going to be 32 minus 24, right? So that's going to be 8 degrees Celsius, right? And I have a blank for C of water. But look right here. We know what that is, right? Because we know the definition of a calorie is it's the amount of heat energy required to raise 1 gram of water 1 degree Celsius, right? And we know that a calorie is 4.184 joules. So we actually already know the specific heat of water. That's never going to be given to you. It's expected that you'll know it, okay? So 4.184 joules per gram degrees Celsius. Okay, we now have enough info to do this problem. So what's delta T? Well, we just calculated it in our chart, right? It's 8 degrees Celsius, right? 32 minus 24. Okay, next. What's Q for the water? Okay, well, we know that Q for the water is equal to its mass times its C value times delta T. And look what we got right here, okay? So that means Q for the water is equal to its mass, which is 150 grams, times its value for C, 4.184 joules per gram degree Celsius, and delta T we already know, right? So check your units. Grams, grams, Celsius, Celsius. We're left with joules, which is what we want. We're trying to calculate Q, and that's energy, right? So we need to have an energy unit. So then you just plug this all into your calculator. Okay. 150 times 4.184 times 8. We get 5,020.8 joules, right? Okay, that's Q for the water. All right, next step. What's Q for the calorimeter? Well, it's just using Q mixed again, right? We need the mass of the calorimeter, its specific heat, and its change in temperature. So we're just going to plug in here. Q for the calorimeter is equal to its mass, which our little chart says it was 5 grams, right? Its C value was 1.95 joules per gram degree Celsius, and delta T is 8 degrees Celsius. So same thing with your units, check grams, grams, Celsius, Celsius. You're left with joules, right? And you get 78 joules. Okay. See how easy each equation is when you have filled out the chart first? Okay. Last step. Now it's the calorimeter equation. Okay. That negative Q of the object is equal to the Q of the water plus the Q of the calorimeter. Okay. So plug that in. Negative Q, in this case, it's a reaction, right? Reaction or object equals 5020.8 joules plus 78 joules. So negative Q of the reaction is equal to, stop it, George, 5098.8 joules, which means that Q of the reaction is negative 5098.8 joules, right? And the negative sign signifies that the object lost that amount of heat energy. Does that make sense? The water gained and the calorimeter gained, but the object cooled off. It lost this. So the signs are really important here. Okay, let's look at our whole thing. Each step was the same equation, right? It's just cumic. That's all we're doing. So all of the math here is cumic, and then knowing the relationship between the object and the water in the calorimeter. Okay? This is all we're going to do for the rest of this time. It's okay. Could be worse. It could be worse. Honest to goodness, the hardest part is filling in the table. Okay? All right. Let's try another one. And you guys are going to do this one this time. Okay? So let me make us a new sticky. Make them a little shorter and fatter. And put our little table in. Okay, so this one is actually going to have an object. Okay, so I'm going to ask you guys just one at a time to tell me where numbers go. Okay, all right, so we'll just go the way our windows are here. And I'm going to start at the bottom of my windows. I don't know how it is. I don't know if all of our windows look the same or what, but okay, let's read it. A 28.5 gram block of an unknown metal is heated to a temperature of 151.7 degrees Celsius. It is then dropped into the same calorimeter that was used in the previous example, where its mass is 5 grams, C is 1.95, the mass of the water is 150 grams. If the initial temperature of the water was 22 degrees Celsius and its final temperature was 24.2 degrees Celsius, what is the specific heat of the metal and what is its identity? Okay, so let's go to the bottom and read through again. All right, Gunnar, you're my first window. A 28.5 gram block of an unknown metal. What do I do with 28.5 grams?
All right, so that's a mass unit, and um, I think it's for, would it be for the objects?
Yep, that's the mass of the object, 28.5 grams. Okay, all right, good job. Phoebe, you're next. A 28.5 gram block of an unknown metal is heated to a temperature of 151.7 degrees Celsius. Where do I put that temperature?
Would that be for T initial for the object?
Yes, exactly right. That is the initial temperature of the object. Whoa, George, why'd you do that? Okay. Right, because everything all three are going to have the same final temperature, right? So this temperature is specific to the object. We have a hot object that was dropped in. Well, that's why you got to read the whole thing, right? It was heated to a temperature of 151.7. It is then dropped, okay? So it's saying I heated it up, then I put it in my calorimeter, okay? You're going to need to draw your own for the problems. So you need to know what boxes you need to have, right? Okay, let's keep going. So let's see who's next. Liam. All right. So it is then dropped into the same calorimeter that was used in the previous example. What do I do with 5 grams?
Did you say my name?
I did. Yep. What do I do with 5 grams? Where does this go?
Um, so use Q equals MCT, and then the 5
We're
gram
not,
is, oh,
yeah, we're not ready to calculate yet. We're just filling in our chart.
oh,
So
sorry.
where,
The 5 grams is used to calculate the heat absorbed by the calorie meter. Calorie meter.
calorimeter. Yep. Okay. So this is the mass of the calorimeter. Okay. All right, Isabel, you're up next. Our next number is C equals 1.95 joules per gram degree Celsius. Where do I put this value for C?
Um, would you put that in temperature initial?
Well, is this just a temperature? Right, this
No.
is a C value, right?
Yeah,
So whose C is this? Who does it belong to? The object, the water, or the calorimeter?
I'm pretty sure it belongs to the calorimeter.
Yep, you're right. Okay, so this goes here, 1.95 joules per gram degree Celsius. Okay, let's see, who's next? Owen. Okay, so the mass of water equals 150 grams. That one's kind of easy. Where do I put that number?
Is that the temperature? No, I'm kidding. It'd be the mass of the water.
Yeah, the mass of the water, right? Okay, we're getting a lot of stuff filled in on our chart, guys. This is good. Okay, so let's see, who's next? Lila. If the initial temperature of the water was 22 degrees Celsius, where do I put that?
You're gonna put that in the initial, in the water section under initial.
Okay, where else can I put it?
I think you would put it on the kilometer.
Yeah,
Calorimeter.
calorimeter. Yeah,
Sorry.
yes. They're always, the water and the calorimeter are always going to have matching temperatures, right? For initial and final. Okay. All right, let's see. Who's my next one? Millie. Okay. The final temperature was 24.2 degrees Celsius. What do I do with that one?
So, hold on. I was about to say you would put that in the final temperature of the water,
Yeah,
but
you're right.
I'm right? Okay. I was just
Okay.
confused because I was thinking that since all of them had to be the same, that it
Yeah.
would be something.
Well, you're right. They all have to be the same, which means I can put it everywhere, right? For calorimetry problems, there will only ever be one given final temperature, and it applies to everything, right? Because remember, the definition of thermal equilibrium is the temperature at which everything has the same temperature, right? We reach thermal equilibrium when there's no more flow of heat, okay? Everything's got the same temperature. So final's always going to be the same in all of your rows, okay? So we've got some empty boxes, right? We've got empty delta T boxes and we have some empty C boxes. So the problem is asking us to solve for the specific heat of the metal, right? So this right here is our unknown, right? That's what we're solving for. But what can I put for C of the water? Can I fill that in? Yeah, Connor.
4.184 joules over grams degrees Celsius, I believe.
Yep, exactly right. Okay. Because it would be 1 calorie, right? That's the definition of a calorie. And we know a calorie equals 4.184 joules. Okay. So we've got delta T's that we need to figure out now. And remember, they're always final minus initial. So for that metal at the top, it's going to be the 22.4 minus 151.7. 24.2 minus 151.7. So we're going to get a negative value here. Okay, negative 127 because the metal cooled off, right? And then delta T for the water is 2.2 degrees Celsius, and so it is for the calorimeter. Okay, now our chart is full. We're going to be able to do all of our calculations really easily. All right, so what's delta T for the water and the calorimeter? Well, we already figured that out, right, with our chart. It's just 2.2 degrees Celsius. Oh, stop that, George. Rude. Boop. Okay. Next, what's Q for the water? Well, it's equal to the mass of the water times C for the water times delta T for the water, right? So we're just plugging and playing here. It's 150 grams times 4.184 joules per gram degree Celsius times its delta T, right? So stop a second and check your units. Grams cancel, Celsius cancels. You're left with joules. Whoa, stop rolling, George. So that's what we want, right? We want our answer to be in joules for Q. So what do you guys get? A number. You get a number. I'm proud of you. What number? Use your calculators, guys. You can do it. There you go. Lydia got it. Okay. 1380.72 joules. Okay. All right. So you guys can probably jump ahead of me. We need to know Q for the calorimeter, right? So we just got to plug in the values from our chart. Okay. So Q for the cal, its mass, 5 grams. Its C, 1.95. And its delta T is the same, right? Okay. So what do you get then? $21.45. 21.45 joules. Boop. Okay. Now we got to use the calorimetry equation, right? Because the heat that was lost by the metal is the heat that was gained by the water and the calorimeter. So negative Q of the metal equals, what did we get? 1380.72 plus 21.45 joules. Okay, what do you get there? Yep, thank you, Blakely. 1402.17 joules. Okay, so we know Q for the metal. So we're being asked to calculate C, right? And if we use QMICT and solve for C of the metal, we just have to divide both sides by the mass times the change in temperature, right? So we just need to plug in here what we got. So we know Q for the metal is 1402.17 joules. And it's negative, right? Sorry, because negative Q is the positive. So Q is the negative. So negative 1402. And then its mass was 28.5 grams. And its delta T was different, right? And the sign matters. Okay. So just thinking about your Q-mixed equation, you can have a negative value for Q because it signifies heat lost. And you can have a negative value for delta T because that signifies heat lost, right? Something cooling down. You cannot have a negative value for mass, and you cannot have a negative value for C. So if you are calculating C and you end up getting a negative number, you need to go back and check because you probably did something wrong. Okay. So yes, thank you, Michael, for calculating that. 0.386. And the units, nothing canceled, right? So I got to keep all of them. But this is what we want. We want to have joules over grams degrees Celsius for a specific heat. Go ahead, Gunnar.
So when we have the negative Q of the metal, that's signifying the heat loss of the metal.
Mhm.
I'm the Q. What is that? Is that the specific heat, right?
No, Q is the value. The value is in joules. So it's saying how much heat
Oh
did
yeah.
this object lose? It lost 14.02 or 1402.17 joules,
Okay,
right? That's how the energy it lost. Okay. So yes, Michael's right. The further part of the question was which is it? What metal is it? And the answer here is zinc. Now, if you look at copper, it's really, really close. But we're going to round up, okay? Not down. So this is zinc. What person finds a 28.5 gram? You'd be surprised. You'd be surprised. My stepdad, Connor's Jaja, he worked at the national laboratories in New Mexico, Sandia National Labs. And when he first worked there, he ran the mass spectrometry lab. And their job was to identify things. So things would be brought and they would have to figure out what they were. And they did a variety of tests on them. Obviously, they did mass spectroscopy, but they also did calorimetry and a variety of other things. So when you have a mystery object, you do all of these tests to figure it out. I'll tell you guys, if this is interesting to you, if you think that playing with this kind of stuff in a lab is something that would be interesting, like an interesting job, look into materials science because it's not a job AI can do, right? AI could analyze the data, but AI could not collect the data. So it's a pretty fun branch of science and also engineering. So after he did that for a long time, the next job he moved on to was telling the CIA how to build secure devices and what they should build them out of. Like, I need an object that can do this. What material should I use to build it? So he was like, I don't know if you've ever seen James Bond. He was Q. Like he was like the guy behind Q, telling Q what to make things out of. Okay. Anyway, all right. So we probably don't have time to do a whole nother problem, but we can definitely fill in a table for another one. Okay. So please use the chart. It might seem a little bit silly, but it's much easier than trying to, at each one of these steps, trying to go back up and figure out which number applies. Because when you've got them written out already, it's really easy. Okay? All right, so oh, wait. We finished that one. Never mind. I guess I didn't finish that one with my other class. Never mind. We'll go on to the next page. All right. So here's the thing about Q for the calorimeter. So in our last problem, we calculated that Q for the water was about 1400 joules, and for the calorimeter, it was only about 21 joules. So the Q for the water is much higher, right? It has a much higher specific heat. It also, compared to the calorimeter, has more mass most of the time. So sometimes we get to ignore the calorimeter because it's so small, okay? Sometimes you're only going to have to collect information about the object and the water, okay? So that makes it easy. Then your equation simplifies to negative Q of the object is equal to Q of the water, okay? So if the problem gives you any information about the calorimeter, it gives you its mass, it gives you its value for C, then you need to assume you need the whole equation, okay? But I would say probably at least half the time, you're going to get to ignore the calorimeter, okay? Any questions about that? It's kind of nice to get to ignore, okay? So let's look at this one. And we'll probably only have time to fill in our chart. And then we can come back to it tomorrow. Okay. Stickums. And chart. Ooh, he's not fat enough. Make you fatter. There we go. Okay, let's read it. A calorimeter holds 188 grams of water at an initial temperature of 23.5 degrees Celsius. A 55-gram piece of metal at 100 degrees Celsius is dropped into the calorimeter, and the final temperature of the water is 28 degrees Celsius. What is the specific heat of the metal? Ignore the calorimeter in this problem. Hallelujah, right? Okay, so I get to ignore you. Meh. We're going to ignore him. Okay. So let's go back to, let's see, who had gone? Lila, Millie, Blakely, you're going to be first. Okay. So a calorimeter holds 188 grams of water. Where do I put that?
Would it go for the mass of water?
Yeah, that one's kind of simple, right? 188 grams of water. Good job. All right, who's next? Kristen. Okay, a calorimeter holds 188 grams of water at an initial temperature of 23.5 degrees Celsius. Which box should I put that temperature into?
Is it the initial temperature of the water?
Yep, exactly right. 23.5 degrees Celsius. Good job. Okay, who's next? Shepherd. A 55-gram piece of metal. What do I do with 55 grams?
That goes in the mass of the object.
Yep, 55 grams. Okay. April, you're next. Okay, 55-gram piece of metal at 100 degrees Celsius. Where do I put 100 degrees?
Would that be the initial temperature for the object?
Yeah, the object, exactly right. Good job, 100 degrees Celsius. Okay, let's see, who's next? Mira. Okay, so it's dropped into the calorimeter and the final temperature of the water is 28 degrees Celsius. Where does that go?
That goes in the final temperature for water.
Yep. Where else can it go?
It can go for the final temperature of the object as well.
Yeah, exactly right. Remember, there's only one final temperature and everybody gets it. Okay? So, what's the question asking? It says, what is the specific heat of the metal? So again, we're solving for the specific heat of the metal. Okay? So let's see who's next. Lydia, what can I put for C for the water?
Was it the 4.184 joules?
Yep, I can put 1.184 joules per gram degree Celsius. Okay, and then let's see who's next. Michael, what is delta T for the object?
That would be negative 72 degrees Celsius.
Negative 72, right? Because that's going to be 28 minus 100. So the negative sign is important. see who's next. Steven, what is delta T for the water?
That would be 4.5 degrees Celsius.
Mm-hmm. And that one's going to be positive, right? Okay. All right. We're ready, right? You now have the information you need to calculate Q for the water because you need the mass, the specific heat, the change in temperature, and you have all except your C value for the object, right? Because the Q is going to be the negative of whatever you calculate for the water. And then you're going to be able to rearrange that equation to solve for C for the object. Okay? All right, guys, this is as complicated as it gets. This whole module was just about this one equation and how to use it in calorimetry. So I highly encourage you to practice a little bit each day. Okay, yes, that's all this module is. Okay, next module, I'm just going to warn you, is a lot more. 13 is a doozy, okay? 12 is not. 12 is very straightforward, okay? I think so, bud. I don't have the answer right in front of me, but yes, I think so. So yeah, all you're going to do is, all right, what's the T for the two, right? And we already calculated them. So T for the water, 4.5. T for the metal, -72, right? And boop, you'll calculate Q for the water. And stop it, George. Rude. Okay. Then you'll calculate Q for the metal. Well, yeah, it's just the negative of what you get for the water. And then you rearrange and solve for C. Okay. So you have the homework is extra credit, guys. This is like the gimme of the universe. All right. Be practicing. I also posted 2 additional worksheets that have 5 calorimetry problems each. So use those. I also gave you the solutions so you can practice that. Okay. Yes, Michael, go ahead. Oh, your hand went up. Maybe you didn't mean to.
No, my computer just glitched there.
You just put your hands in the air. Okay.
I tried to raise my hand. What's the hardest module in your opinion?
I think module 13, personally. I don't mean to scare you guys, but here's the cool thing about module 13. So we know that creation is fallen, right? We know that because of sin, creation is fallen and things don't work exactly the way they're supposed to anymore, right? Like we know that our bodies can get diseases. We know that things in the earth can become polluted, etc. And so we are actually going to be doing the math that shows chaos coming. Okay. It's actually a very cool thing to be able to do. You can do the math, sort of. So module 13 is about a concept called entropy, which you may have heard of before. It is the tendency of systems to move from order to disorder, right? You can see it, say, in your room. If you clean your room and everything's really nice and tidy, and then you don't do anything for a week, right? Like you just live in your room and you don't make a conscious effort to pick up, what does it look like at the end of the week, right? Not like it did when you had just cleaned it, right? So that's a great demonstration of entropy, right? Disorder is our tendency. So we're going to figure out the math that shows it happening in chemistry. It's actually very cool, okay? But it's conceptually very difficult. Mathematically, it's easy. Conceptually, it's difficult. So reading the questions and figuring out what you're supposed to do is challenging, okay? All right, but this module, let's focus here. This module is pretty easy because you have one equation, Q minute, right? And a lot of the time you're going to be allowed to ignore the calorimeter. And so if you can figure out Q for the water, which you'll always be able to do, you'll know its mass, you'll know its value for C, you'll know its change in temperature, then you know the Q value for your object or your chemical reaction that's happening in the water, right? Hi. Okay, guys, that's it for today. So do a little bit of practice from the 57 practice problems I gave you and come tomorrow ready to do some more of this calorimetry stuff. Okay? I will see you tomorrow. Bye.